In this module, we will learn how to calculate the moment of a force about a point from a two-dimensional perspective. So here's a question. Look at this wrench, look at the pair of forces, look at the point where you think the action is being taken, which is the bolt in this case, and notice that the forces do not pass through that point. This is unlike the problems that we've seen before. We're going to explore the idea that the effect of this pair of forces is called a moment or a torque, and it's a measure of the sense of rotation or twisting that the forces cause about that point. And I want you to think about other examples that might be similar. So abstractly, we can think of a force vector and some other point in space called P. In this case, we'll imagine that the plane of the screen is the plane where everything is lying. And we're going to define the moment of the force F about this point. The first thing we do is we extend the line through F. We then determine the perpendicular distance from P to the line through the force. And then we calculate the magnitude of the moment as the force multiplied by that perpendicular distance. You might remember in physics, moment is F times d. The clarification is that we're using the perpendicular distance between the point and the line of the force. And if you want to think about P as being called something, we can call that the base point. So how come in the previous slide I was careful to talk about the magnitude of the moment? It's because we're now going to introduce the sign convention that tells us which way is positive. So recalling that the point P and the line through F create a plane, let's now visualize an axis with this double-headed purple arrow perpendicular to that plane. And there's something that you might know from physics called the right-hand rule. And that means if I take my right hand and wrap my fingers around that perpendicular vector, my right-hand thumb points in that direction, and the rotational direction that my fingers wrap indicates the sense or the positive direction of the moment. And as before, the calculation is now force times perpendicular distance, and now I'll call this the moment because now I'm calling this the moment relative to that convention. And if you want to see this further, look at the line that I drew perpendicular from P to the line of the force. And imagine that I initially had the force F attached to that line, and I gradually move the force along its line of action. And you can see how that line would rotate, and that rotation has the same axis as my right-hand thumb. So if we visualize this back in a two-dimensional viewpoint, meaning directly down at the plane defined by P and the force F, I can again illustrate the perpendicular distance between the point and the line of the force. And now I'll use my right-hand rule. In this perspective, it looks counterclockwise. And now define the moment of F about P as F times the perpendicular distance. And I'll introduce this symbol using the I and J unit vectors with a counterclockwise curled arrow around what would be the k-axis or the z-axis to illustrate our positive sign convention. Now, one interesting thing, if I slide the force along its own line of action, it does not change the moment about the point P or about any other point. And can you see why that's true? Now, what would happen if I reverse the force direction? Notice that I also negate the value of the moment. If I maintain my arrow as counterclockwise, the F really wants to go clockwise, so I have a negative value about the counterclockwise direction. On the other hand, if you also reverse the sense of the moment arrow, then you also come back and report that as a positive value. This is very similar to what we've done with other things with X and Y components. Just be sure you're trying to be consistent with your sign convention and your labeling. One other interesting fact about moments is very important. A special case is when the line of the force passes through a point. It turns out that the moment of the force about that point is 0. And I'd also like to ask you to think about why that's true. Now, in some situations, the d perpendicular distance is not given, so we have to work around other kinds of information. So for example, suppose I gave you some distance L, which was on some other line, not parallel to the other lines that I've shown you here. And I define these two angles alpha and beta. I think it's now clear from what we've learned in trigonometry that the moment of the force around the point P is ultimately force times perpendicular distance, but now that perpendicular distance can be seen as the distance L times the cosine of alpha, or the distance L times the sine of beta. Also, in some cases it might be useful to slide the force into another position, again along the same line of action. And in this case, what we'll do is we'll decompose the force in components relative to the line that we're given, in this case relative to the line along L. And if I draw that second angle vector, or that angle symbol, I think that's clear that's the same as the angle beta. So now I can make components of F relative to that system. And if I now recalculate the moment about P, I notice that the component F cosine beta is going through the point P, and therefore does not cause any moment. But now I have the F sine beta is perpendicular to the line where L is drawn. And if I do the calculation, I now have F sine beta is the force component multiplied by L, which is now that perpendicular distance. And if I rearrange terms, I have F times L sine of beta, which is back to where we were before, F times D perpendicular. It all works out to be the same final result. The only difference is a matter of the procedure based on the kind of information that you might have. And we'll see some examples like this throughout the rest of the course. So here's a very quick example. Suppose you have someone on the end of a diving board and you want to know what is the moment of that diver's weight about the anchored point of the diving board, which is here point P. So let's illustrate this. There's the weight of the diver. There's a set of axes. In this case, I am giving some 3D perspective to illustrate what's happening. I'm going to draw a corresponding set of unit vectors I, J, and K. And I think it's clear, though, that the moment is in the plane of I and J in this case. So it'll create a moment about the K axis. And so I'm going to draw my right hand thumb and fingers around that axis. And the calculation is force times distance perpendicular. And notice that the distance from W to the point P is L. So I take 125 pounds multiplied by 5 feet, and I get 625 foot-pounds.